while David gets a face shield, it's really good to be back here with a in-person talk. We were just discussing before the talk that most of us had forgotten exactly what to do, how to set it up. It's been a really long time. So yeah, glad to have everyone back, and a huge thanks to our speaker for actually agreeing to give an in-person talk. This is particularly exciting for me in that I've actually been collaborating with Modibo since middle of last year, but we've never actually met in person. So it's kind of interesting that we both have an in-person seminar, but also I get to meet a collaborator who I've never met in person because of the pandemic. So we are really delighted to have Modibo Camara speaking today. So Modibo is an economics PhD student at Northwestern. He was telling us yesterday that he started off doing his undergraduate at Penn, and he went and met his faculty advisor and told him that, well, I want to do something at the intersection of economics and computation. And according to him, his faculty advisor said, well, there is no intersection of economics and computation. You have to do one or the other. And so he ended up doing economics and then sort of slowly discovered this whole area of econ CS. And this makes it really interesting because he's one of the few people in econ CS. So most of econ CS are people who are coming from computer science, sort of trying to apply the tools to problems in economics. Modibo is one of the very few people I know who's really coming from a pure economics background, bringing sort of the thought processes and kind of the philosophies of economics, but then sort of taking on a bunch of ideas from computational thinking and sort of getting it back to economics. And this makes, so even though this is an econ CS talk, it's a very, very different flavor from most of the other research I've seen in this area. So he's been working at Northwestern with Jason Hartline, but like any good economist, he's mostly been just working on his own on a bunch of problems. And the high level, I guess, he's been thinking about, the way I think of it is he's thinking about why people behave the way they do, and then what people can do as designers. Once you know why people behave the way they do, what you can do as a designer in order to sort of incorporate that. But he's sort of been combining, this is a very old area of thought in economics in general, but Modibo's been sort of introducing some very interesting ideas from computational thinking to these questions. And so today he's going to sort of tell us about how you should think about mechanism design in this context, but he has a lot of other interesting work on thinking about just behavioral models and also how you can learn these from data. So please talk to him more about this if you're interested, but in the meantime, over to you.
Thank you, Sid. Yes, I'm very, talking with the mask is getting an interesting echo, so if you can't hear me or anything, please let me know. Yeah, I'm very glad to be presenting here, very glad to be invited and talking to all of you. So, I am an economist, right? I do talk with CS audiences with some frequency, but I've never talked with a broad general interest OR audience. So if there's anything I can do to clarify things during the talk, please let me know and we'll adjust as needed. So this work is joined with Jason Hartline, who is in Northwestern Computer Science, and Alec Johnson, who just is a PhD student who just graduated, also Northwestern. Okay, so at a high level, we can think about economic policy, social policy as being successful or failing according to whatever objective you might be interested in. And these successes or failures are influenced by at least two factors. One is environmental details, right? So things like consumer demand or labor supply, right? Getting the tailoring the policy to the environment itself will be important for success. Second, individuals' beliefs about the environment, right? So if you are a policymaker, you will often care about how the individual will respond to your policy. Those responses will, from an economic perspective, typically depend on what they believe about the world, things like inflation expectations and so forth.
Sorry, one quick thing. Can you share your screen on Zoom?
Oh, yeah, that's a. Let's see.
Awesome.
So
Thanks.
yeah, hopefully you can all see the slides on Zoom. Thank you. Okay. Now, get rid of that. Okay. Now, the two factors that I mentioned so far, right? They're, in many settings, sort of inherently dynamic, economic conditions can evolve in unpredictable ways over time. Individuals can learn and adapt over time. So naturally, ideal policies should also be dynamic, and ideal policies will adapt to their environment over time. For instance, we can think about minimum wage laws that are sort of adapted to market conditions, both in terms of time, right? What are market conditions today, and in terms of space, what are market conditions in my particular town as opposed to my state or my nation. Okay, so at a very high level, right, we can ask, so can we develop dynamic policies that adapt to their environment over time? And particularly, we want to answer this question, with at least 2 or 3 desiderata. So first, we want to be able to answer this question without making strong assumptions on how the environment evolves. So we want to use I think this is shifting. I might, maybe I can put on a mask again. I think this is fun. Let's see. Yes. Okay. Right. So can we develop these dynamic policies without making strong assumptions on how the environment evolves? Particularly, we want to use what's known as a prior free or adversarial model. And second, can we do so while making only relatively permissive assumptions on agent behavior, right? So as an economist, I'm sort of critically interested in how people behave, people responding to their incentives. So agent behavior is going to be critical to this talk. In particular, when we're making assumptions on agent behavior, we want to relax the typical kind of assumption made in economics, which is basically that everything about the environment is known in advance. And we want to think about agents that are learning over time and adapting to their environment. 2 particular desiderata that we want to have within this case are what I call ex ante optimality and ex post feasibility. And ex ante optimality basically says that whatever behavioral assumption we're making, it should be something that agents should optimally satisfy. Right? So we don't want to assume that agents are doing something that is not in their best interest. Likewise, and this is sort of more of a CS perspective, we want to make assumptions that are what I call ex post feasible. So we want to actually be able to provide algorithms that solve the agent's problem to the degree sort of required by our behavioral assumptions. Okay, so our framework, sort of at a very high level, and we'll get into more detail later, we're going to be thinking about a repeated interaction between a policymaker and a single agent. After each interaction between these two, a hidden state of nature is going to be observed, and this is going to affect payoffs. It's a very simple model so far, right? We're going to be thinking about this as a sort of a minimal viable case, right? So we're assuming only one agent. We're assuming very rich feedback about the world, right? These things, are not relevant to every application we might be interested in, but it's going to turn out that a lot of the fundamental questions that we need to resolve are going to be present even in this setting. Okay, so just a very brief overview of the contribution, and then we'll get into more detail. So standard behavioral assumptions that are common in work on, for example, learning and games, like no regret assumptions, are going to be insufficient in our setting, in the sense that we're not going to be able to come up with good dynamic policies without making stronger assumptions, and in the sense that they're going to allow for odd behaviors that we want to rule out. We are also, given this, we're going to want to refine existing behavioral assumptions to what we call counterfactual calibration. And at a high level, what counterfactual calibration is doing is saying the agent should fully and consistently exploit any private information they have. Okay? Defining information and sort of understanding how to map this into the observed history is going to be a key challenge of this work. We're going to propose what we call a calibrated policy that adapts over time, using historical data on the states of the world. And we're going to give conditions under which the policymaker's regret from following our calibrated policy is bounded. So by regret, we mean relative to the best-in-hindsight static policy. Okay, this is related to a number of different literatures in economics and computer science. The literature on robust mechanism design, paper by Sylvain Chassang from 2013 is especially relevant. Work on data-driven auction design, whether that's through online or batch learning models. In auction design, typically the agent is not, the agent's learning problem is not as severe as in our setting, right? If you are familiar with auction design, agents typically know their own values. and there exists ex post incentive compatible auctions. So the kind of agent learning questions that we study here are not as explored in this literature. Regret-based behavioral assumptions have been used in quite a bit of work here, just three very selected examples. And there's also some work that looks at sort of learning in incomplete information games, where both the policymaker and the agent are. Happy to discuss any of these papers in more detail if you want offline. Okay, so let me talk about the basic model. So I'm going to first talk about the stage game. So a repeated game is what we're eventually going to be discussing, a repeated interaction. Stage game is just one iteration of that repeated game. I'm going to refer to the stage game at some different points in this talk, so I'm going to color code the slide green when I want to talk about the stage game, so you don't get confused with the actual game that I'm discussing. So in the stage game, policymaker is going to set some policy P in some finite set script P, send some message M. This you can think of as an announcement to the public in some finite set M. Agent is going to choose a response R. There's going to be some hidden state of nature S. Payoffs for the policymaker and the agent are going to depend on the policy, the response, and the state, not on the message. And as I said, we're assuming that all relevant spaces are finite.
Well, everything's very high level now, but what's the relationship between M and P?
Yeah, so we'll see sort of how what role M plays later on in the talk, but basically this is if the policymaker has some information about the world that he wants to convey to the agent, offering a message, sending a message, making an announcement is one way to do that.
And P is made public as well, of course. Right?
P is made public as well, yeah. So P is the payoff relevant choice, and then M is just in case you want to provide the agent with any additional information.
So M may be private?
Private, so it's the policymaker sending the message to the agent. So since there are only two participants, I guess it would be
Okay.
Mm-hmm.
So is R a function of M? Or is that why it doesn't go into the utility?
Yeah, so that's a very good point. So we think about this as the agent observes the policy and the message, and then chooses a response. So the strategy for the agent in the stage game is a mapping from policy space, message space, to response space. And the message doesn't enter into the utility function directly because, if you think about like the Federal Reserve like issuing a forecast on some economic indicator, that doesn't directly impact you. It might indirectly impact you through the knowledge that you have or how other people react to that information. Yeah. Okay. Anything else?
So I guess
does the state of nature remain fixed or as a dynamic?
So right now we're still talking about one iteration of a repeated interaction, but later the state of nature will change. Yeah.
So I guess I was asking, is the message, so the policymaker does not have additional information about the state of nature. Like this is what we are thinking of as what is unknown to both agent and policymaker.
Yes.
But you're not talking about the priors about, okay. I guess you've not said anything about where the state of nature is generated from.
Right, yeah. And generally we don't think of the policymakers having any particular information about nature, but later on we'll see that an important part of the mechanism is calibrated forecasts that we're going to provide the policymaker with, and we'll see how we'll basically want to publish those forecasts to the agent in case it has any relevant information. But we'll see in more detail how that's used. Okay, repeated game, just a stage game repeated t times. In each period, little t. First, the policymaker sets a message, policy PT and a message MT. The agent will choose a response RT after observing these, and then at the end of the period, the state ST is observed and payoffs are realized. So here you see the assumption. Basically, there's very rich feedback about the world. Everything that's payoff relevant you observe at the end of the period. Policymaker's mechanism is going to be a map from the history to policy and message in the present period. And the agent's strategy is going to be a map from the history, the policy that was observed, the message that was observed to a response.
Okay.
Yeah?
I'm sorry, is this state a function of, reacts to the agent's response? Or?
The state we think of as exogenous. So it's really just some arbitrary sequence of states. We don't know in advance what it is. And it's not going to react at all to actions. Yeah.
Do both the agent and the policymaker observe the payoffs?
And say again?
Do both policymaker and agent observe the two payoffs?
Yes, so they both observe the state S, and they know the utility function, so they can infer payoffs. Fs.
Oh, they actually, and the payoff is just, it's a deterministic function, right?
Yes, it's a deterministic function of the
Okay.
policy, the response, and state. Okay. So now, and I'll give you an example of a sort of setting in a bit. Let me just finish up the discussion of the repeated game by talking about the objective, right, the benchmark we're trying to achieve, the policymaker's regret. So I'm going to define it. First, 2 bits of notation, right? As before, we think about R1 through capital T. Capital T is the number of the horizon of the game, as corresponding to the agent's responses to the actual policies, P1 through PT, that the policymaker chose. So this is P1 through PT is the output of the mechanism, right? We might also want to talk, and we will want to talk about how the agent's behavior would have changed had we used a different mechanism or a different sequence of policies. So in particular, we're going to be interested in fixed policies P, where you choose the same P in each period. And we're going to let R superscript P denote the agent's responses if the policymaker, instead of using their mechanism, used the fixed policy. Okay, so now we can define policymaker's regret. Policymaker's regret is going to compare actual policies, the performance of actual policies, with the performance of the best-in-hindsight fixed policy. On the left-hand side here, you have the utility under the best fixed policy P. What does that mean? Take the time average, the average over time, of the policymaker's utility from the policy P in each period, the agent's behavior if you use the static policy P, and the state ST, which is, again, fixed. And we take the maximum over that performance across all static policies. On the right-hand side, we're going to subtract from that the policymaker's utility under the actual policies, the mechanism that we're proposing. So here we have the utility average over time from the policy PT that the policymaker chose and the response that the agent had under that mechanism. Okay. Final note here. You might be aware there are algorithms sort of in single agent or sort of single participant settings that can guarantee no regret assumptions. Can guarantee no regret in the sense of vanishing regret. They don't apply to this setting because the behavior of the agent depends on the mechanism chosen by the policymaker. Okay, so when you choose a policy in a given period, you need to take into account how that would have affected the agent's behavior. Generally, right, if we make no assumptions at all about the agent's learning algorithm or the agent's behavior, the strategy, potentially the behavior could change quite substantially based on policies that you choose in a given period. Okay. Any questions on this slide before I move on?
When you take the max over P, what information do you have to do this? Like, do you know all the states that would have been realized? Like, do you know all the STs when you do this maximization? Or?
Yeah, so it's once we've completed the game, we've done T iterations, right? We observe the state in each period T. We observe the hypothetical policy and the physical. Yeah.
What does the policymaker know about how the agents behave? Like, should I think of RT to be a function of PT? Or not?
So far, I have not I guess this notation doesn't highlight the dependence of RT on the sequence of policies chosen by the policymaker. This is just the benchmark, so we won't have to worry about what the policymaker knows or not, right? Because we're not yet defining the algorithm for the policymaker, the mechanism. I am going to, so the results that I show you do not require knowledge of the agent's strategy. So whatever regret bounds I show you are going to apply for any agent strategy as long as it satisfies the behavioral assumptions that I'm going to make.
Yeah. So do the agent's responses to a fixed policy P not depend on the states?
Yes. Yeah. So the agent strategy will depend on the state history as well as the policy history. Yeah.
How does the history play a role in the pair of functions?
So the history of the state. So if we think about the agent as the policymaker and the agent will have their utility in the repeated game will be just the average of their utility in each period. And their utility in each period will depend on the state of nature. I might be able to clarify that a little bit more in just a slide when I talk about like a particular example. Okay. So I just want to have an example in mind, a simple example that I can refer back to that fits into this framework. It's going to be a problem of price regulation. We're going to think about a firm and a regulator. So the firm is going to be producing a single indivisible good at some cost, and at some price, in order to maximize profit. So fitting this into the model from before, we think about a firm's response as saying, okay, well, the firm knows their own price, so the response is going to be a function from the cost. Sorry, the firm knows their own cost. They're going to map the cost they observe in the present period to a price that they want to set for the consumer. And the state S is going to describe the firm's costs and the buyer's value from the good, right? Of course, the buyer's only going to purchase the good if the value exceeds the price. The policymaker's role here is to regulate price in order to maximize welfare, which I'll define in a second. The policy P is basically going to consist of a price floor and a price cap. The outcome, sort of whether or not a sale occurs, is going to be this indicator sale. A sale occurs if two things hold. First, the buyer's value exceeds the price, so the buyer decides or wants to purchase. And second, that the price satisfies the regulation, so it's between the price floor and the price cap. Profit is just whether a sale occurs times the price minus the cost. And welfare is going to be whether the sale occurs times the value of the buyer minus the cost. So welfare is going to be indifferent with respect to who ends up with more money. It's just going to want to make sure that if the trade is efficient, it occurs. Okay. Yeah, and then next we can sort of move on to the repeated price regulation setting. We now have a sequence of buyers T, each one arises with the value Vt. The state St, as before, the value and cost at a particular point in time, is observed at the end of the period T. The assumption that the buyer's value is observed at the end of the period might be a strong one. We can actually replace that with an indicator for a sale occurring, being observed. Basically the price, which is the agent's choice, and the price floor and price cap, which is the policymaker's choice, will presumably depend on the observed history of the state's actions. Okay, so that's just a running example. Any questions on that before I move on?
Just to be clear, the values are exogenous here. So there's right. No sort of strategic aspect by the buyers.
Exactly, yeah. So it's a very simple model. We just have basically a buyer arriving at a particular point in time exogenously. They have some value, then they disappear forever. Okay.
Just to be clear, so the agent here then is the firm that's deciding how it maps from cost to price?
Exactly. So the buyer is basically non-strategic, the firm is the agent, and the regulator is the policymaker.
And the cost here comes from like it's also exogenous.
Also exogenous, right? It just happens your suppliers in a given period are more expensive.
Is the policymaker trying to maximize welfare while the agent is trying to maximize cost?
So the policymaker is trying to maximize welfare, and the agent is trying to maximize profit. Yeah, exactly. And of course, in the repeated game, this will be average over time. Okay, cool. So then we can move on to the next part, which is the agent's behavior. So this will take a bit of time because, again, one of the sort of key contributions of this work is to try and even understand how do we think about rational behavior in an environment where we're not imposing any kind of stochastic assumptions or prior knowledge. So just a quick preview of the definitions that I'm going to be sort of introducing. These two are existing definitions in the literature. We first think about sort of a set of behaviors that satisfy no regret. We can refine that to behaviors that satisfy calibration. We're going to further refine this to behaviors that satisfy counterfactual calibration. Okay, and you can think about calibration as saying you're going to fully exploit any information revealed through your behavior. We'll formalize that. And counterfactual calibration, it says, in addition, you're going to consistently exploit that information regardless of what the policymaker does. In addition, we're going to also talk about a lower bound in regret, so non-negative regret. And basically, we're going to argue that the intersection of counterfactual calibration with non-negative regret corresponds to like a non-clairvoyance property that basically says the, so in the running example, for instance, the firm is no better at forecasting costs or demand than the policymaker. Which in that context actually might be violated, right? But non-clairvoyance will basically rule that out. Okay, and another sort of quick high-level intuition that I hope you sort of maintain with you as we go into a bit more detail. The issue that we're basically going to be dealing with here is that in our adversarial model, the agent might appear to be more informed, might appear to be capable of better forecasting the state than the policymaker. Okay? And we're going to basically, I just want to very briefly illustrate why that might be an issue by analogy with like a classic fable of the tortoise and the hare. Okay? So I'll define no regret assumptions, but basically no regret assumptions are ones that are sort of more common in the existing literature. And we're going to think about no regret assumptions applied to an uninformed agent as being effective. Right? So no regret assumptions make sense when the agent is uninformed. Similarly, we can think about this as a statement that says a tortoise trying to finish a 1 kilometer race is going to finish that race in an hour. Okay? So if we ask a tortoise to finish a 1 kilometer race in an hour, it can do it potentially, but it really has to hustle, go a straight line as fast as it can. If we ask an informed agent to satisfy no regret assumptions, we're going to run into trouble. Okay? And the analogy here is suppose we asked a hare, right? Hare is faster than tortoise. Informed agent is more powerful than an uninformed agent. Suppose we asked a hare to travel 1 kilometer in 1 hour. It can do all kinds of things, start and stop, take detours, and still satisfy our assumption. So no regret is not going to be strong enough to handle, to control the agent's behavior. What we want to do in the analogy is say, okay, well, let's calibrate the benchmark to the speed of the animal, right? So if we say the hare has to finish the race in 2 minutes, it has to go straight ahead. So similarly, what we want to do is we want to say the informed agent is going to satisfy no regret conditioned on whatever information she has. So with that very high-level intuition, let's go down into a bit more detail and understand what this terminology means. Okay. So first I want to define something that I'll call the agent's conditional or contextual regret. Okay. And this regret will be defined with this covariate called information, and basically different definitions of information are going to correspond to different behavioral assumptions. No regret, calibration, and counterfactual calibration. The agent's regret conditioned on information IT. It's going to be, somewhat, if you haven't seen regret before, it's somewhat similar to the policymaker's regret. Left-hand side here, we're saying, okay, maybe I'll take a step back. So we think about the agent as looking back on her behavior, right, at time t. In every period where she had information I, some particular realization, she asked, what is the best-in-hindsight response in that period, and across those periods? Okay? So whenever I have information I can switch my behavior to some new response given by h of I. Okay? H is a function from the space that information takes values in to a response. So on the left-hand side here, we say, okay, suppose that in hindsight, I optimally mapped my information to some response. This is the average performance that I would have under those modified responses. On the right-hand side here, we just see the agent's actual utility from her responses, R1 through RT. Okay. And again, the modification rule H is going to map information to responses H by T.
Okay. So the information IT is supposed to be available to the agent at time t. Correct?
So not necessarily. So what we're defining here right now is just basically a benchmark, right? So the benchmark I can define at the end of the game when everything is observed and IT. There's not actually going to be, we'll see in a bit more detail, but IT is not necessarily something that the agent will observe. We can still judge her by sort of how well she might have performed had that information be observed. And then the question is whether this is a relevant benchmark because it relies on information the agent might not have, and I'll argue that it does.
So is there a natural way to think of this information if it's not something available? So what would be a good example of it?
So information, what we'll be using is for the purpose of defining calibration or no internal regret or no soft regret, the information is your own past behavior. Okay, so the idea here is sort of to use a different example, right? Suppose that I'm a forecaster. I'm doing weather forecasting, my forecast is calibrated if whenever looking at all the time periods where I predicted a 50% chance of rain, empirically there was actually 50% chance of rain. Okay? And so it's saying my regret conditioned on predicting 50% chance of rain should be low. Any other questions? I'll sort of give more details on what information IT is.
One quick thing about, so earlier you said when you were defining the counterfactual, only the STs were known when you took the maths. In the case of the policymaker.
Okay.
In this case, is the sequence of PTs also known when you take the marks?
Yeah, so I'm thinking about this, and maybe I was a bit imprecise before as well, I'm not sure. So I'm thinking about this as, a deity essentially looking at this game, having observed everything that occurred at the end of the horizon, and saying, okay, well, in principle we can compute all these things given our sort of.
But this H is like a fixed function you apply for all time. So this is, should I think of this as like a general, like more expressive than a best fixed policy? Or
Yes,
best
exactly. So
Okay.
if we just wanted a best fixed policy, we could concentrate on constant functions H, which are the same in every period. Functions H that don't depend on information, where the information varies.
So that's why you mean this is a stronger bench, or this is more difficult benchmark.
Yes, exactly. Yeah. Okay. So the first benchmark I want to define, no regret. This is the bread and butter. In our model, it's actually even like just because of what our model is, it's an extensive form game. It's a little bit different than what you might be used to. So regret is basically the regret conditioned on public information, which the public information is the policy and the message in the present period. Okay. So we think about the agent in a given period. What do they observe? They observe the policy, they observe the message. If there's any information conveyed through the choice of policy or the message sent to the agent, you might want to incorporate that into your behavior. Otherwise, no regret is just saying at the highest level that regret is going to 0, it's vanishing as the number of periods goes to infinity. So I want to sort of illustrate to you why no regret is not going to be a good enough assumption for our purpose, and then I'm going to move on to calibration, and then later to counterfactual calibration. To illustrate that, I'm going to sort of use this game of rock, paper, scissors, like a very simple game, to convey the idea that the agent might appear to be better informed than you might think, just from how we wrote down the model. Moreover, that any information she does have is going to be revealed through her behavior if she is sort of acting in a reasonable way. So let me just describe the game first. So rock, paper, scissors, we think about the agent and H as playing rock, paper, scissors. The policymaker doesn't have like a meaningful role, but you can choose whatever kind of role you'd like. I don't need the policymaker to do something to illustrate this point. So basically, in each period, nature is going to be rock, paper, or scissors. We have here, I believe, 12-period game. Basically, the first period, state is rock, second period is paper, third is scissors, and then it repeats. The agent is going to have an action space, a response space, that is also a choice of rock, paper, scissors, and basically you want to beat nature at the game. Okay, so let me describe a possible sequence of behaviors that we could see that would satisfy a no-regret assumption. This is what I'm going to call an uninformed strategy, just for now. And it's going to basically be a strategy where there's no correlation between the response and the state. So for example, here we see the responses. Again, each period you choose, so first period you choose scissors, second you choose rock, then rock, paper, and so forth. Basically, I just did this using random number generator. So the agent's action has, it's literally by construction independent of the state of the world. We see that they get, in some periods they choose, they choose scissors against rock, they get a bad outcome. Sometimes they choose rock against scissors, they get a good outcome. Right? Overall, on average, they're going to get an expected value of 0, which in this case is going to be the best in hindsight possible. Sorry, the best possible in hindsight. Okay. Let me get my computer charger. Okay. Here we go. Thanks. Okay. Okay, so here we see, okay, this agent is by construction uninformed. We don't see any systematic correlation between the response and the state. Let us consider a different case. In informed strategy, here there's going to be perfect correlation between the response and state. So suppose that the agent's behavior, for whatever reason, turns out to be rock, paper, scissors. That actually should be slightly adjusted. So let's suppose that this one is paper, this one is scissors, this one's rock, so forth. Basically, you want the winning strategy in each period. And basically, the outcome will be in each period you get a good payoff because you win. Now, this is going to satisfy no regret, right? It's going to be a very good strategy. It's not necessarily one we think the agent should be able to sort of guarantee, but it's always possible that her sequence of responses and the sequence of states happens to be one where it's correlated. Okay, so with that in mind, we have this idea that past behavior reveals your private information.
Sorry, but here, this wouldn't be able to be implemented by your functions of H that you have defined before, because the agent doesn't have information, right, about the state when it constructs R.
So H will be a map from an object information, which I'll define in the next slide, at least for calibration. Yeah. So let me address that on the next slide. I think that's a good question, but we'll use it for this now. Okay. Okay. So we have this idea that behavior reveals information. So it makes sense to say, okay, well, if behavior reveals information, can we ask for no regret conditioned on behavior? That's what internal regret is going to do. Just regret conditioned on information revealed on path. So information revealed by the agent's behavior given the mechanism that was chosen. As before, it'll include the policy and the message in the present period, and it'll include the response. Again, this is not something that the agent does not observe her response in any meaningful way, but for the purpose of defining benchmark, we can include. Calibration, of course, is going to say that internal regret goes to 0 as the number of periods goes to 0. Cool. So next, basically, I want to show you that no regret is going to allow for strange behaviors that calibration will rule out. Here, we're going to think about a slightly different state sequence. So we'll start with rocks for the first half and then paper for the second half. Remember the tortoise and hare analogy. I'm going to define a strategy that corresponds to the tortoise. This is one where the agent is uninformed, optimizing in some sense, and satisfies no regret. And it basically says, choose paper in every period. Okay? You basically do as well as you can. The first periods you get a good payoff, and the second periods you get second half you get a neutral payoff. Okay, so that's uncontroversially within the bounds of what we might want to allow for. Now let's think about the lazy hare strategy. This is going to appear to be informed. It's going to be, however, suboptimal, and it's going to also satisfy no regret. So here again, so we think about the agent's responses as starting with rock in every period and ending with scissors in every period. So clearly through the behavior, the agent is able to distinguish between the first half and the second half of the game. In the first half, the agent is going to do something suboptimal, which is, well, you're able to distinguish. You see it's always rock, and you're still playing rock, which is not good. But then later on, you're going to be choosing the optimal thing, scissors. So basically, think about, if the hare is starting off the race by doing something very, going very slowly, taking a break, whatever, and then finishes strong and still manages to beat the hare, beat the tortoise. This is essentially saying, okay, the agent is going to start off by doing something suboptimal, silly, right? And then end up by, outperforming by using their private information about the world. Okay. So lazy hare strategy does not seem like something we want to call rational, not something that we want to consider, right? If you're able to distinguish between the first half and the second half, then after a while, you should be able to learn that, well, first half you should play paper. Okay, calibration is going to rule this out because we're saying, let's condition your regret on the action that you took. If you took the action scissors, well, then you're conditional on that. You're optimizing, right? You're always choosing, well, you're choosing the right one. And conditional on taking the action rock, you're not optimizing. So the agent would, in hindsight, prefer to change from whenever she plays rock to playing paper.
Maybe I was slightly confused at your statement that this is no regret, because how does this agent's like how does it fit into, like, you define no regret with respect to a benchmark, either like it's not constant policy, but it's also not with respect to a function h of known information.
Right. Yeah. So the I guess the known information here. So it was the policy, the message. For these examples, I'm not really. I will in a second, but I'm not so far including an active role for the policymaker. So you might as well just think about the policy and the message as being constant. Yeah, but
So
if you
here
want
the
to.
hair is not allowed. I mean, it's playing a non-constant policy.
Yes.
Yeah.
Yeah.
So then okay.
So here's an algorithm for the hair. That is a dumb algorithm, but it exhibits behavior shown here without requiring any additional information, which is regardless of the history, for the first 6 period players play rock, and then the second 6 periods play scissors. Okay?
Oh, I see.
You're just ignoring the history. So it happens to be the case that that behavior is justified by the sequence of states that occurred, right? And we don't know anything about the sequence of states, so it could always be the case that it's justified. It's not necessarily a good algorithm in the sense that, you know, if the states were different, you would no longer guarantee low regret. But if you're very confident in your worldview, then you might do this.
So yes, I'm confused on the informed. So here the informed, the agent is not learning anything but state. Is the agent attempting to learn the state or not? No.
So the agent could be, but I guess the algorithm I just described is one where the agent just does the same thing regardless of the history. It's one where we interpret the agent as, you know, for whatever reason, they understand that the first 6 periods are different than the next 6 periods, but they don't need to learn about the world through the data to get that.
Okay, I still confused. So in this second step here, the second example, why do you say called informed? Because it's agent.
Yeah. So my interpretation of this is, well, formally what we can say is there is empirically a correlation between the response and the state, right? The response and the state. But my interpretation of this, right, which is just an interpretation, is that we can think about this as an agent that happens to understand that the first 6 periods are different from the second 6 periods. Happen to understand something structural about the world that distinguishes the beginning from the end.
I'm sorry, I'm also a little bit confused. So I'm trying to interpret a system like this as involving learning, right? So if I'm an agent, then I'm trying to learn something as the time goes, right? And this way I would improve my policy and make it better, right?
Right.
So what exactly am I learning here if I'm an agent?
So the agent, the algorithm that I just described is not learning anything. But it is allowed by our no regret assumption. So if we want a model where we force the agent to learn, we need to do something that's tighter, stronger than no regret, right? I guess what I'm saying is that this algorithm here for the agent, where the agent is not only, she's not learning, and she's doing something that's kind of bizarre, that's one that is allowed by no regret and ruled out by calibration. So that's an argument to refine our assumption to calibration.
Why is this no regret? Why doesn't he regret playing the rock?
Oh, because the best-in-hindsight fixed policy is to always play, action is to always play paper.
So no regret relative to a best fixed
Yeah.
in hindsight policy.
Exactly, right. And so calibration is going to refine that to say, not only do I want to have the best-in-hindsight constant action, but I'm going to say, okay, I want to say, conditional on choosing rock, I prefer to play rock. Yeah. Okay.
I'm still a little bit confused about informed and uninformed, and you say that one is no correlation and the other is perfect correlation. So is there any partial correlation?
Sure, yeah. So we can think about, this is like the most extreme example just to convey the idea, but we can think about any kind of correlation between the response and state as conveying potentially information. Okay, so just a quick impossibility result. So I talked about calibration. I'm going to argue that calibration still is not enough. Okay, so and I'll give you some intuition for this on the next slide. But based on the proposition, there exists a strategy for the agent. Okay, like we just talked about some possible strategies. There exists a strategy for the agent where no mechanism that we might come up with can guarantee a non-trivial bound on the policymaker's regret across all sequences of states where the agent strategy is calibrated. All right, so just in somewhat more succinct words, calibration is not enough to guarantee low regret mechanisms. And in particular, this is true even if we knew the agent strategy. So even if we know the agent strategy, we would not be able to come up with a good mechanism. So just again, some very quick intuition for why this, actually, that'll be in the next slide. What I want to do next is I want to refine calibration to counterfactual calibration. And then on hopefully the following slide, I will give you some intuition for why that is. Okay, so counterfactual calibration. So calibration depends on internal regret. Counterfactual calibration depends on counterfactual internal regret, which says we're going to condition the agent's, we're going to condition regret on information revealed through her behavior, both on path and off path. So behavior revealed on path means if we run the mechanism we're proposing. Off path means if we ran one of our n different fixed policies. So R to P is going to be the response of the agent if we had just chosen the fixed policy P1 in each period. If we get rid of this, this is calibration, but we're going to add in the counterfactuals. Counterfactual calibration says that counterfactual internal regret, CIR, is going to 0 as t goes to infinity. And now just an example to illustrate what calibration is allowing, that we want to rule out. Take again the sequence of states, which is just rock in every period, then paper. Here's an algorithm for the agent. It's a stupid algorithm. You'd never want to run this, but it's something that is allowed by calibration. Okay? Looking at the history, if the policymaker followed the mechanism that we propose, play the tortoise strategy. So in every period paper, you get no regret. You also get calibration because you chose the same action every period. If the policymaker deviates from that, or say plays a fixed policy, we're going to play what we'll call like the active hare strategy, right? We have the lazy hare, now we have the active hare, which says, okay, we're going to be able to distinguish between the first 6 periods and the second 6, but now we're going to do the optimal thing. So the first 6 periods we're going to play paper, then the next 6 periods we're going to play scissors. Okay? So we use our information, but we use it fully. This is going to be calibrated because you're doing the X plus optimal thing, right? So if we chose this mechanism, if we chose our mechanism, if we as a policymaker followed our mechanism, the agent would be calibrated. If we deviated, the agent would be calibrated, so the agent's learning algorithm is calibrated. But it's dumb because the agent reveals information through her behavior in one counterfactual that she does not exploit in another. So counterfactual calibration is going to get around this by saying, even when we run our mechanism, we're going to evaluate the agent's regret by conditioning on the behavior, the information that she reveals off path. Yeah.
What does the mechanism mean?
Oh, mechanism is a strategy for the policymaker, so it's a function from the observed history to a policy in the current period.
Okay.
Yeah.
And what is the difference between following a mechanism versus following this policy?
So I'll give you a mechanism in a second, but suppose there's some strategy for the policymaker that we just designate. That means you follow that. Fixed policy means you play the policy P in each period, irrespective of the history. So fixed policy is like a different mechanism. It's like a constant mechanism. It's probably not one you'd want to use, but yeah.
So what is the policy maker? I mean, in this game, there's no. I just feel like we can talk about this policy maker in this situation.
So you're right. I have not very clearly identified a role for the policymaker here, basically because it's irrelevant for the purpose of getting intuition. The only thing is whatever the policymaker could do, any model you want to write down. It might be payoff irrelevant, so it might be totally irrelevant to anything. The agent, however, is going to observe the policies chosen by the policymaker and can condition her behavior on those choices. And calibration is going to allow her to condition her behavior on those choices in a weird way. Counterfactual calibration will rule that. Okay, so that's counterfactual calibration. The only remaining assumption that I want to introduce is what I'll call non-clairvoyance. You could also call it uninformedness, but I think non-clairvoyance is a bit clearer. It's a combination of counterfactual calibration and non-negative regret. So lower bound on regret. Very quick intuition. Counterfactual calibration says at a high level the agent is fully and consistently exploiting any private information she has. Non-negative regret is saying that the agent is not outperforming the best use of public information. If you're fully exploiting private information and you're still not outperforming the public information, the private information is not very useful. So that's the sense in which the agent does not appear to be especially better at forecasting the state than the policymaker. Okay, so I have, I think, 7 minutes left. So I'll talk about the calibrated policy. Very high level, in each period t, we're going to form a probabilistic forecast of the state st. We're going to assume that the agent shares this forecast, and then we're going to choose an epsilon robust policy based on that forecast. I'll define what all these terms mean in the next slides. And basically, informally, the result is going to say that this calibrated policy works well when the agent is not clairvoyant. Okay, epsilon robustness. Note the color green. So we're getting back to talking about the stage game. So this is different from the repeated game that we've been talking about. Okay, and basically this will be a fictional game that we're going to use as like a subroutine in our algorithm. We're going to assume that the state is drawn from some distribution pi s. We're going to say that a mixed response, which is a distribution of responses of the agent, is an epsilon best reply to some policy p if the agent's optimal utility, the agent's optimal payoff, is at most epsilon greater than the utility she obtains from her mixed strategy. The policymaker's worst case utility, given an epsilon best reply, just says worst case WC. Let's evaluate our payoff of the policymaker across, in the worst case, across all distributions, mixed responses that satisfy the epsilon best reply property.
What's the relationship between epsilon robustness and epsilon best?
Yeah, so epsilon robust is what I'm going to call basically a policy that maximizes the worst case utility. Yeah. Thank you. Okay, last slide notation. Policymaker's best case utility, we define worst case utility, we can define best case utility given an epsilon best reply. Just says let's come up with or evaluate our payoff with respect to the best case epsilon best reply. Cost of epsilon robustness says, so COR, cost of robustness, says let us subtract, so best case utility minus worst case utility. Now I can define the mechanism. Epsilon now will, so again, this is blue, it's a repeated game. We're getting back to the repeated game. Epsilon is a robustness parameter. This is something we can set in the algorithm. We're going to assume access to, and we can construct using known results, calibrated forecast pi tilde. It's going to have some grid with the delta. It's just a discretization. The policy that we're going to choose is the epsilon robust policy in the stage game, assuming that the forecast is correct. So we look at the worst case payoff in the stage game where the state is drawn from the forecast, and we maximize our worst case payoff with respect to the policy. Finally, message, we're going to publish the forecast for the agent. So if there's any information embedded in our calibrated forecast, this is information we're just going to publish it freely to the agent, and we can expect the agent to take it into account. It might be the case that there's no information, which is totally fine. All right, so that's a calibrated policy. Assumptions, first, so to get the regret bound. First, the agent is non-clairvoyant, which again is a combination of counterfactual calibration with non-negative regret. And we're going to make a technical assumption, which I don't have quite the notation to state here. But it's going to say that information that the agent might possess, which is in the stage game, useless to her, under any policy that you might choose, that information is not going to be harmful to the policymaker. Right? So if we gave the agent just like noise that is totally useless to her but might be correlated with the state, the agent acting on that noise, essentially breaking ties based on that noise, won't affect the policymaker's payoff. Okay, and then we get the following regret bound. So the policymaker's regret from the calibrated policy is less than the following, and so I'll interpret these terms. The first term is the cost of robustness, evaluated in each period according to the policy that we chose and the calibrated forecast, plus sensitivity parameter, which is just 1 over epsilon. So the higher epsilon means more robustness, so less sensitivity, times 2 terms that capture miscalibration. First one is going to be the agent's miscalibration, or the counterfactual internal regret, which measures counterfactual miscalibration. And the second one is going to be miscalibration of our forecast. Okay. So, of course, if the agent is, counterfactually calibrated, this term will be going to 0 as the number of periods goes to infinity. This term will be going to 0, if we set the width grid parameter at the right rate. This term, it depends on the model. There's some models where even if you have a common prior or commonly known distribution, the agent might be different between 2 different policies, where one policy is really good for the policymaker and one is really bad. So there might be what I call a cost of robustness, even if the agent is best applying, even in standard models. But if that's not present, which in many models we think of that as not being present, then this will be going to 0, as epsilon goes to 0. Okay, key trade-off. We increase epsilon, this tuning parameter. It's going to reduce the sensitivity to miscalibration. So we're less concerned about if our forecast is correct, and we're less concerned about if the agent is fully rational. But it's going to increase the cost of robustness, because we're going to introduce more robustness in our policy. Yeah.
So the main thing the policymaker is try to identify the true state. Am I right? The information forecast is the estimation of the state.
Yeah, so it's a density forecast of the state. Yeah.
Right. So you have guaranteed the agent, the policymaker, what the forecast wise has a certain level of accuracy. Is that guaranteed by delta or something? Your pi delta is the estimation, right? Your estimation
yes.
of the state.
Yeah, that's forecast, right? Mm-hmm.
Forecast.
Mm-hmm.
So is there something guaranteed to the true one or something? What's the
So,
forecast, arbitrary forecast cannot be good, right?
Exactly. Yeah. Okay. That's absolutely correct. So I didn't go into this in much detail, but we can talk about just as we talk about calibration of the agent strategy, we can talk about calibration of forecast. And basically, there exist forecasts that have a calibration property where, again, sort of conditional on making a probabilistic prediction. Empirically, it turns out that probabilistic prediction is justified. So we're not just using any arbitrary forecast. We're using forecasts that have a nice property that's been identified in the literature.
So for that matter, the agent can also separately forecast. Because agent has an inverse positioning than the policymaker to forecast state.
Yeah, so the agent can independently forecast. The agent could use the policymaker's forecast if they want. Yeah.
So your assumption here, the agent has no better way to predict it.
Yes, that's what the non-clairvoyance assumption is saying.
That's
so
what?
The non-clairvoyance assumption that I made. So it's saying basically the agent does not need to use the policymaker's forecast, but there's no reason for their forecast to be any better. Okay.
Maybe you're going to talk about this, but is the intuition that by backing away from the optimal policy in the stage game, the policymaker is less sensitive to sort of these kind of miscalibrations, to miscalibrations in these forecasts or mistakes.
Yeah. So I guess that comes in, if I'm understanding correctly, in the bound through the coefficient here, right? So of course, if epsilon is very large, right, then it doesn't matter quite so much how large these terms are because the whole expression will be smaller. So if epsilon were infinity, then miscalibration wouldn't matter at all. But of course, setting epsilon to infinity means you have probably a really bad policy. Okay, so I think I'm over time, but let me wrap up. Conclusion, just very briefly, we talked about the non-clairvoyant case. You might also want to consider the case where the agent does have private information. Several approaches. We assumed already that basically it doesn't exist. You can assume that it exists, but it's well understood. That's also totally fine. We have an extension in the paper that just says, okay, let's optimize against the worst case information. That's something that's done in the economics literature. And we have work in progress that's saying, can we adapt to private information over time? Can we actually forecast the agent's information? and then some future directions in theory and application. Okay, thank you.
Okay, I guess we have time for some questions. Also on Zoom, if anyone wants to jump in. Maybe I'll start off with one. So, just looking at your regret bound, there is no obvious way of deciding what's like an optimal epsilon to set. Like, is there some kind of natural like Pareto trade-off between these, or?
You know, I would say the bound that we have here, it applies very generally, right, to basically any finite policy space is subject to the one technical assumption I gave you. So in particular, this 1 over epsilon term, which is motivated by the following lemma, that's probably not tight, right? Like we can get it in like a super general sense, which is why I think it's powerful. But if you have a particular application you're interested in, you could probably get a better bound, right, by taking advantage of structure in that problem.
Yeah. Okay.
So I would not like suggest taking this bound and saying let's optimize epsilon according to it, because in whatever application you're interested in, you might be able to sort of take advantage of the structure of that problem and do a lot better. But yeah, so we can of course get an asymptotic result in this case, and we have an explicit finite sample bound.
I don't know if you mentioned it, but is it easy or hard for agents to compute like a kind of fractional calibrated strategy?
Great question. So there exists so just to answer the question formally, there exists an algorithm that achieves counterfactual calibration with the same rate of convergence as we can achieve calibration. So if you...
It's complicated, it's a nice algorithm, it's a very difficult algorithm.
Yeah, so I mean, there are relatively nice algorithms that guarantee calibration, and we can basically take those. So even add a little bit more structure. Here's a way to satisfy counterfactual calibration. Come up with a calibrated forecast of the state, like I described, for the policymaker, and optimize according to that calibrated forecast. That will satisfy calibration. It will also satisfy counterfactual calibration because it does like the totally reasonable thing, which is I have the same forecast regardless of what the policymaker does, right? And as long as you have that property, counterfactual calibration is just the same as calibration, right? So counterfactual calibration is really just trying to guard against like these really weird outcomes that calibration allows for, but it's actually for a lot of reasonable kinds of behavior, counterfactual calibration is not really stronger than calibration.
But that puts the work on the policymaker for making a good forecast, or?
No, so the agent can just run her own calibrated forecasting algorithm. Yeah. So if you can get if there exists a calibrated forecasting algorithm that's as quick or efficient as you like, which hopefully there is, because there's existing work on it, then there exists an algorithm for the agent that satisfies counterfactual calibration, which happens to make use of that forecasting.
I had a question about the definition of non-clairvoyance.
Sure.
So there's two conditions, right? There's the counterfactual calibration regret goes to 0, I guess? Is that what counterfactual calibration means? Okay.
Yeah.
And then non-negative regret, is that with respect to like regret against the best fixed policy, or regret with, is it like what kind of regret is the non-negative regret?
Yeah, so it's the most naive form of regret. It's this one, where you're just using public information.
Okay, yeah. So then that's like saying they don't have any useful information above and beyond.
Exactly. Well, so it's non-negative regret is, so that's exactly right. I just want to highlight, non-negative regret is saying you don't outperform the best use of public information. Counterfactual regret is saying that whatever information you do have, you are exploiting. So it's a combination of those two that gives meaning to non-negative regret. Yeah. Yeah.
Will you consider extending to multi-agent cases?
Yeah, so I think I had a slide on the end, like a bullet. I think it's an interesting direction. I think there are a number of interesting directions. Maybe we can pull them up.
Yeah, but will it be much harder?
Yeah, so it depends on how you do it. It depends on the particular setting. I think there are some settings in which, especially if you have many agents, right, a large number of agents, then I think in many settings it should not be particularly hard to adapt the results that we have here. In settings where you have a small number of agents that are sort of really thinking about how to manipulate each other, that's going to be more challenging. Yeah. I think it's an interesting open direction. I think I could identify some cases where it's not hard to adapt these results, but I can also identify cases where it might require a lot more thought.
Yeah, homogeneous with heterogeneous.
Any other questions?
Okay, it's time for Modibo again.
Thank you.